we are working our way up to doing calculations. And we're going to do calculations using formulas, using conversion relationships, using measurements. And we want to come up with a set of rules that will help us figure out how to quickly determine how many digits to write in our answer. And these are just real quick estimations on how to write it. So before we can even talk about what to do in a calculation, we have to learn how to count these things called significant figures in your measurements. So we have two broad categories of measurements, relationships, things like that. We have one type which is an exact value. That can come about from counting. So if I ask you to count the number of pennies on the screen, well, there are 10, and there's no doubt about that. There are 10. If in the middle of lecture I were to stop and count the number of students in my classroom, as long as I'm careful, I can know how many students there are, and there's no doubt about that. You can have exact numerical relationships. These four are exact relationships. There's no doubt. It doesn't change. 100 cents in a dollar, that doesn't change. The 1 minute equals 60 seconds doesn't change. That's a definition. That's important, and we'll learn how to deal with that later in calculations. We also have inexact values or relationships, and measurements are always inexact. You cannot have an exact measurement. It does not exist. If I take this as my measuring instrument, that's my fake ruler, and then I have a piece of paper, and I'm measuring the length of it. So I lay that down on my ruler, and at first glance, I see that it's at least 1.7 centimeters long. This measuring instrument is marked every tenth, and so if you look at the end of that piece of paper, it's a little bit past the 1.7. But it's not really appropriate for me to just write 1.7. For metric measurements, unless you are told something different about the measuring device, the rule of thumb is you go one digit after your markings. So this little ruler has markings every tenth of a centimeter, so I'm going to estimate to the 100th because that's in between the two markings. And to my best estimate, it looks like it's 1.74 centimeters. Maybe 1.73, but that's what I can do, 1.74. Those digits are important. That last digit is really important too. The last digit in a measurement depends upon a few things. It depends upon the measuring instrument and how good it is as far as the markings. It also depends upon the person using the measuring instrument. We'll come back to this. You can have inexact numerical relationships. 1 mile is approximately 1.6 kilometers. I can do better than that. 1 mile is approximately 1.61 kilometers. I can do better than that. 1 mile is approximately 1.609 kilometers. All three of those are inexact. Which one you use can affect how you write your answer if you were converting from one distance unit to another one. Uncertainty or error. It's a parameter that characterizes the dispersion of the values attributed to a measured quantity. That is a mouthful. Let me try a different way. Let's go back to that measurement. I wrote it as 1.74 centimeters. Now think about what's known and what's not known about this. The 1 is known. That piece of paper is at least 1 centimeter, but it's not 2. So the 1's fine. The 7, it is at least 1.7 centimeters. It is less than 1.8, but it is 1.7. I estimated in between two lines, and I took that as about 4/10 of the way between those tenths. So I estimate that to be 1.74 centimeters. Anybody who would look at that measurement would understand that the uncertainty in the measurement is in that last digit, unless you're told something special about the measuring instrument, but you're not, so you have to assume that that last digit is where the uncertainty is. Don't mischaracterize error as being a mistake. It's not. A lot of times we use error and uncertainty as being synonymous with each other. Uncertainty is really the better term. Finally, significant figures. It's any digit that contributes to a value's precision, the meaningful figures or digits in a measured or calculated quantity. We need to learn how to count these significant figures or digits because it can affect how we write our final answer. When you count them, you start at the very left and work your way right. And you start your count as soon as you hit a non-zero digit. So let's go back to this 1.74 centimeters. I start at the left. My first digit on the left is a 1. Well, that's not 0, so I start my count. That is significant. The 7 is significant. And the 4 is significant. All three of those are significant, so I have 3 significant figures. Anytime you see the abbreviation SF, assume that it means significant figure. Let me give you 4 more examples. Before I give you those 4, let me do one thing. I'm going to take the units off. Now, with significant figures, there have to be measurements involved somehow, so you need units in there somewhere. But we're just going to look at the numbers, so pretend there are units on all of this. Okay, now let me give you those 4 examples. What do you notice about these 4 examples? You notice that there's at least 1 0 in all 4 of those compared to the very first example. Correct. You have to be careful as to how you handle the zeros when you count significant figures. So let's do those rules. The first rule. Zeros between non-zero digits are significant. Let's pull up that 210.6 example. I start at the left and work my way right, but I notice right away, oh, there's a 0 in the middle. Now, is that significant or not significant? It's between 2 non-zero digits. It's significant. Think of it as just being part of the measurement. It just happened to be a 0. Since I start with a 2 and work my way to the 6, all 4 of those digits are significant. Rule 2. Zeros at the beginning of a number are not significant. They are placeholders. So the next example I had up, 0.089. Well, you start your count on the left, but you don't start your count really until you hit your first non-zero digit. So those zeros I ignore. Those zeros are what we call placeholders. They're there to make sure that you understand that the number is 0.089 and not 0.89 or 89 or something like that. But as far as significant figures go, we don't count them. You don't start your count until you hit the 8. 0.089 has 2 significant figures. Third rule, zeros at the end of a number and after the decimal point are always significant. 175.000. The balances in our lab are good to 3 decimal places. So if I were to put something on the balance and it read 175.000, that's what I would write down for my data. I'd say the mass of this is 175.000 grams. Don't leave off the zeros. It's important. By including the zeros after the decimal place, you're telling somebody that you can actually record the mass to that many decimal places. So those zeros are significant because they're at the end of the number and they're after a decimal place. Now, end of a number, that's important. So start at the 1, start counting. You have 6 significant figures there. And then the last example I gave. Zeros at the end of a number that does not have a decimal point are not significant. They are placeholders. So that's 6,000. There's no decimal place there. So those 3 zeros at the end, they are not significant. They're there to make sure that you understand that this is supposed to be 6,000 and not 6. When you count your significant figures, you start at the left, work your way right. There's no decimal place. 6 is the only one you have. There's 1 significant figure. And let me summarize these. Remember, pretend there are units all over these things. That last one, the 6,000. Now, while there is one significant figure, if that were the result of a calculation, it's possible there would be more than one significant figure if it's the result of a calculation. But I'm getting ahead of myself a little bit. That'll come later.